So today we will continue the last, as I said, the last part of the power calculations. But before that, let's summarize the main things that we did so far. We know that power P is equal to VRMS, IRMS, cosine theta V minus theta I. So to find the power, and of course this is in watt, we multiply the voltage magnitude by the current, cosine the difference between the two angles. And we said that if our load is pure resistance, only R, so this is your I RMS, and this is your V RMS. So in this case, your P will equal to, again, the V RMS, the I RMS. Now, the cosine, because we have here only a resistance, so the difference between the two angles is 0. So we have cosine of 0, which is equal to 1. So this is equal to VRMS, IRMS. I don't need to write RMS all the time, because this is the default. In power calculations, we only use RMS value. Now, if we have an inductor or capacitor, we have shown that the power in this case will equal to 0, because the difference between the angle is plus minus 90 degree. So you will have no power. And we said that the inductor and the capacitor will have a different form of power that we will not talk about in this course. Another important thing, that okay, what if I have a resistance and an inductor? Okay, so the resistance part will consume the power P. This will not consume, but an overall there will be consumption here. As far as we have a resistive part, then there will be a real power consumption. And we said that the loads, generally speaking, they are either pure resistance, like heaters, or like a washing machine, inductive load, resistance, and inductor. So the resistance is always there. So for every load that we know, there is a consumption of real power. Goes up or goes down, depends on the value of R, but real power is consumed in every load. Now, some loads, they don't have they don't have inductive part, and some have. So those loads will affect, as we will see today, if you have this inductive part, how it will impact the power consumption, the losses, etc. Okay, so let's move now for the last topic that I'd like to cover, which is called the power factor. What is the power factor? The power factor is nothing but this cosine theta v minus theta I. So we give this as a name. We call it the power factor. Okay, so it means that the power P is equal to V RMS I RMS times the power factor. Okay, so sometimes we give you the power factor, not then I don't need to give you the angle. If I give you the power factor, then I don't need you to give it. But there is another important information. It has to come with the power factor, and we'll see why this is important. Now, the power factor could be leading if the current leads the voltage, or lagging if the current lags the voltage. We mentioned before in the previous set of notes, and please go and refer to this, we have two different types or three different types of load: inductive, capacitive, or resistive, pure resistance. If the load is resistance, then the voltage and the current are in phase, so that there is no leading or lagging. Now, if we have a capacitive load, we say that the current leads the voltage, or the voltage lags the current. But we always use the current as our reference. So the word leads and lags, it depends on the current, not on the voltage. Okay. Now, as I mentioned here, so if I have a Z impedance that is capacitive, then the power factor will be leading, as we will see in the coming example. And if Z is inductive load, then the power factor will be lagging. So if I tell you that the power factor is lagging, it means that I have an inductive load. If I tell you that the power factor is leading, then we'll have a capacitive load. And we mentioned that the nature of the loads are either resistive or inductive. There is no leading power factor, but there is one application for the capacitors in the power system. I will just touch base on it in a very, very shallow way and at the end of today's lecture. So let's assume that we have Z equal to this 7.78 plus 7.78 J. So it is a resistance in series with an inductor, and we have a voltage applied. Now I don't write the RMS because now this becomes the norm. RMS is the norm, is equal to 110 angle of 0. Now Z, this is in rectangular. I can convert that into polar using the website that I showed to you. So it has an angle of 45 Z, and it has a magnitude. Now if I want to find the current I is equal to V over Z, which is, this is Ohm's law. So 110 angle of 0 divided by Z, which is 11 angle of 45. So we'll see that the voltage has an angle of what? Minus 45. So if I want to draw the vector diagram for this, the voltage will have an angle of 0. This is your V. And the current will have an angle of minus 45. This is your I. So here what we meant by the current lags the voltage. The current comes behind the voltage, okay? So this is very important thing. So for inductive load, how do I know it's inductive? Because of the plus sign. Remember, the inductor, it's plus j omega L. The capacitor is minus j over omega C. So the sign of the complex number will tell me if this is an inductor or a capacitor. Okay, so all comes together. Inductive load, it means that the current lags the voltage, and hence the power factor here, we call it a lagging power factor. And the power factor is cosine theta V, which is 0, minus theta I, which is minus 45. So it is 0.707, and it is lagging. Now, why we have to write this? It's not just the value. In the coming example, it will show you this. Now, let's try to visualize more. What do we mean by lagging? So here, when you see that the voltage has a 0 crossing, the current was still there. Okay, now after some time, when the voltage goes up, the current reaches the 0. So this is the lagging effect. Okay, so the current comes after the voltage. The voltage leads and the current lags, but we don't use for the when we say lagging power factor, we always refer to the current. Now let's reverse this and replace the capacitor with an inductor with exactly the same value, but now the only difference will be the sign. So we have a capacitor and a resistance. So this load now becomes capacitive. This is the value, same voltage. Now let's see the current. I equal to V over Z. V is the same. Now Z has a minus 45. And now the current has a 45-degree leading. So if I want to draw again the phasor diagram, this is my voltage V. This is my current I. And here is this 45. Now, if I want to calculate the power factor, again, it is theta V minus theta I. And we get exactly the same value, 0.707. Exactly the same value. So the only way to distinguish if this is a capacitive load or an inductive load is the second word here, leading or lagging. So this is why in the power factor, it's not enough to tell me that this is the value of the power factor. And of course, the power factor is between the power factor, clearly because it's a cosine angle, is between 1 and 0. It is always positive, and between 1 and 0. Okay, and we'll see what is the impact if we have close to 1 or far away from 1. Which one is better for us? Is it better to have a high power factor or a lower power factor? We will discuss this in few slides. So here how it look like, the leading. Okay, now it is the opposite. Now when you look here, See the zero crossing here, the current zero cross, and the voltage is still there. The voltage will take some time before it reaches the zero crossing here. Okay, so the voltage reaches the zero crossing or reaches the peak before the voltage. So it leads the voltage. Now back to the question I just was asked here. Here, when you look here, the voltage reach the peak before the current. The current reached the peak after that. This is why we call the current here lagging, and we call the current here leading, because it reaches either the peak or the zero crossing before the voltage. The voltage come after that. Hopefully that's uh, clarify your question, Ro. So it is the zero crossing. Now we can convert that into the angle, and the angle is very clear. When we have the phase shift, if the current is negative with respect to the voltage, means the current lags the voltage. If the current is positive with respect to the voltage, then it becomes leading power factor. Now let's put everything into perspective. Now in the power question, what we have usually three components. We have a generator, which is nothing but a voltage source. Usually that we don't know the value of it. I mean, this is how a typical power problem. Then we have here connected the generator by a cable. Could be pure resistance or resistance and an inductor. So we have here the line. This is called the line or the cable. Because the generator, you have to connect it to the load via a cable. So it has certain Z. I will call this is Z of the line. And then we learned that the load is either resistance or resistance in series with an inductor. But so overall, the load of the house, you can easily say that it's a resistance in parallel with the inductor. So this is your what we call the load, what we consume the power, and this is we call it Z of the load. Now, usually we know the voltage here at the load. This is the problem, typical problems here. This is unlike the circuit problems where you know the supply. Usually we want to find the supply. So usually we know the voltage here at the load side. Call it V load. Now from V and Z, we can find I. Once we know I, and this is known, then we can find V at the supply or V at the source. So this is a typical, we had an example about that. Okay, now this is your voltage here. This is your current. So the power that is consumed at the load is equal to V at the load times I times cosine theta V minus theta I. Okay, so if I know V, I know I, then I can find P and I can find cosine theta. So if I know P and cosine theta or the power factor, this is another way, and I know V, then I can find I. So I can, instead of having the load as such, I can give you the load as such. This is the second type of problem in power calculations, and this is what we will see now in the coming two example. We have Vs that we don't know, similar to this. We have Z line, same thing. We have V at the load, so this is given to us. But now instead of giving you this is as a Z, I will give you this as a P. So I will give you the power P and the power factor. So I will give you these two values. I will tell you this is leading or lagging. Now, once I know V, I know P, I know power factor, I can find I. Here, I can find I using Ohm's law. I is equal to V of the load divided by Z of the load. So the key point is to find the current. So here the current using this formula, I is equal to P of the load divided by V at the load times the power factor or cosine theta V minus theta I. So in this case, or in this case, I found I. Once I know I, This voltage is known. This voltage is known. I need to find this voltage drop, and then I can find Vs. So in both cases, your Vs will equal to the V at the load plus I times Z line, either in this approach or in that approach. Now, I itself, it has to be a vector. And here is something extremely important that you have to know. I is a vector. Now, when we divide V by Z, then you will have I and theta I here, or automatic, because Z is given to you as a complex number, and V is given to you as a vector. So we divide them, or as in polar format, divide them, change both to polar, you will get I. Now, when you do it here, this is a scalar, so you will just get the magnitude of I. So you need still to get the angle. How to get the angle? From the power factor. Remember, what is the power factor? The power factor given to you, which is cosine theta v minus theta I. So if you take the inverse of this, so take the cosine inverse of theta v minus theta I, will give you theta v minus theta I. And theta v is given to us, then you can find your theta I. So in both cases, you have to find the current as a magnitude and as an angle, and then your problem is solved. And let's see an example. This is a very typical exam problem. So let's read it carefully. We have P at the load. So this is a load. This could be a house. This is 20 kilowatt consumption at zero point 0.8 power factor lagging. This could be a house, but with, let's say, a lot of inductive loads like an AC and these type of loads. They have, because power factor zero point 0.8 is a little bit low. And power factor zero point 0.8 lagging. The voltage here at the load, as I said, always you know the voltage at the load is 220 angle of 0, and usually we have it as an angle of 0. It doesn't really matter, but it's easier when you give it to the 0 as a reference, because the power factor angle is the difference between the angle of the voltage and the angle of the current. So let's assume this angle difference is 30. Minus 30 if it's lagging. So if the voltage is 0, then the current will have an angle of minus 30. What if the voltage is 10? Then the angle of the current will be minus 20. So there is always this minus 30 difference. So this is why we always use the voltage there as reference. We say this is our reference voltage. So we give it an angle of 0 for simple calculations. That's all. Then ZL is 0.09 plus J 0.3, which is this one, this is the line. This is the cable that is connecting the generator to your load. Determine the voltage and the power factor at the input line. Here, I want to find what is V and what is the power factor here. Okay, so and here all the values are in RMS. So that I will make sure that to write this statement in the exam so you are not confused. Okay, so every time the power question, it is actually an RMS value. Okay, so P at the load, this is the key formula, is equal to V at the load, I of the load, cosine theta V minus theta I, or the power factor. So IL, the current that go through this circuit, this loop, is equal to PL divided by VL and times the power factor. And everything is given to us. And this is always the case. This is 20 kilo divided by VL is 220 volt. And the power factor is 0.8. So if you do the calculation, this is 113.64. And let me tell you that this is the mistake number one in the book in power calculations. Students just take this and apply KVL. No, you have to find the angle. I will write it down here. You have to find the angle. You are not yet done. How to find the angle? Okay, we see that the power factor is equal to zero point 0.8, which is equal to cosine theta v minus theta I. Okay, so taking the cosine, so cosine inverse of zero point 0.8 is equal to 36.9. Okay, and this is equal to the theta v minus theta I. I just take cosine inverse of these two sides. Cosine inverse here give you the angle. Cosine inverse of here give you the angle. Theta v minus theta I. Theta v is equal to 0. We know that. So your theta I is equal to minus 36.9. And this is in line with what we know. A lagging power factor, it means that the current lags the voltage. So if the voltage angle is 0, the current angle has to be negative because it is a lagging power factor. So now my current I is equal to 113.64 angle of minus 36.9. At this stage now here, power calculations is done. And now it's a simple circuit. So I know the current, I know the voltage here, I know everything. I need to find Vs. So what is Vs? KVL. So we'll apply here just KVL. That's all you need to apply. So Vs is equal to I times the 0.09 plus J 0.3, which is the voltage drop here, I times Z, plus the voltage between these 2 points, which is 220 angle of 0. So I know the impedance, I know everything. Now becomes a simple circuit question and without doing all the calculations. So this becomes equal to 249.5 angle of 4.8 or 4.9. Okay. So this is your voltage, uh, which is what is we want to calculate. Okay, now we want to find the power factor at the input to the line, which is at the source. What's the power factor? Is equal to cosine theta v minus theta I, which is equal to cosine 4.8 minus the angle is the current is the same, so it is minus 4.9 minus 36.9, and this is equal to 0.746. This is your power factor. And if you do this, you will be losing at least 1 to 2 marks. Why is that? Calculation is correct, but there is something missing here. If you don't write the following statement, or you don't do something here, you will lose 1 or 2 marks unnecessary. What do you think is missing here? Okay, excellent, excellent, excellent. Good, William, good, Grace. You have to write here if it is leading or lagging. Now it's obvious it's the lagging. Why it's lagging? Because the voltage has an angle of 4.9, the current has an angle of minus 36.9, so this is lagging. So you have to write this here, otherwise you lose a mark. Because as I said, when you give me the power factor, could be leading, could be lagging. It's two different values. You have to tell me that you understand that this is an inductive circuit and always the power factor will be leading. Okay, so this is the answer here in details. You have it there. Now let's have the last example in our notes. And here in this example, we will see the impact of the power factor. So it says find the power and the voltage supplied by the power company determined how it changes if the power factor is 0.9. So we will find the power here by the power company supplying to your house. This is again 88. This is a huge, this is a building. It could be like a 3-story building. Okay, so we have like 6 apartments or let's say 4 apartments. Okay, so this is not a simple house. Simple house are like about 10 to 20 kilowatt. So this is a huge load. So it would be like a different story line. I mean, multiple story. Okay, and here the voltage is a bit high, 480. Usually we use this voltage in large loads. So basically it could be like usually this we call it industrial voltage. So 220, 120 volt we use it at our houses. 480, 240 we use it at factories usually. Okay, so we want to see the impact. If the power factor was 0.707, we want to see the impact of this. And to see the impact, I want to find the power loss. I will calculate the power loss. Now here the line between the supply and the load is only resistance. There is no inductor. It could be modeled as only resistance or is a resistance in series with an inductor. So I want to see if we change the power factor, and in very, very brief, I will mention how we can change the power factor in very little. We want to see what is the impact of that. So assume that we change the power factor to zero point 0.9, how this will impact our calculation. Okay, now this is to start with, this is very similar to the previous question. So we'll find I, the current, which is equal to the power divided by the voltage and the power factor. Same, very similar. So this is 88 kilowatt divided by the voltage is 480 and the power factor is 0.707. So my current is equal to 259.3 amp. Okay, and from this you can find the angle. Now we need to find the angle. So cosine theta v minus theta I is equal to 0.707. So cosine inverse of both, take both sides. So theta v minus theta I will equal to 45. Okay, so this is your 45 angle. So your theta I is equal to minus 45. Why minus? Because it's a lagging power factor. So we know the current. Now we can find your Vs, which is the 480 angle of 0. And someone may ask, why is it as angle 0? We said that this is a reference voltage. Okay, so even if it's given, we can assume it equal to 0 plus I times 0.08. Now, I, your current, is given to us. The current here, your I, is equal to 259.3 with angle of minus 45. So we have everything. So your Vs will equal to 495 angle of minus 1.7. So this is your voltage. Now, what will happen? I will come back here in the comparison, but let's see what will happen if the power factor now goes to be or become zero point 0.9. So obviously, if the power factor increases, what will happen to the current I? I equal to P. It's the same amount of power. I don't touch the power. The power stays the same. The voltage stays the same, divided by V. So the only thing that changes is the power factor, which becomes zero point 0.9. This becomes 88 kilo divided by 480 times zero point 0.9. And if you do this, this is equal to 203.7. Okay, and the angle, your angle here, theta v minus theta I, will equal to the cosine inverse of zero point 0.9, which is 25.8. So your theta I is equal to minus 25.8, and hence your the current I 203.7, angle of minus 25.8. Okay, so your voltage Vs, exactly the same as here, the same formula, is equal to 494 angle of minus 0.82. So let's now examine what is happening here. Okay, the voltage at the source, little bit of a change. It was when the power factor 0.707, it was 495 angle of minus 1.7. Here it becomes 494 angle of minus 0.81. That's not really a big advantage. Okay, but let's look to the current. The current that goes into the line here is 259.3. It drops to 203.7. Let's see the impact of this on the line losses. In the P loss, which is I squared times R. This is the P loss of here. This is the resistance. So let's see the power loss here. This becomes 259.3 squared times R, which is 0.08. And if you do that, you will find that the P loss is equal to 5.378 kilowatt. This is a loss in the power system. If you see the power loss after changing the power factor to 0.9, so this is equal to, again, I square R, but now the current drops to 03.7. Everything else is constant. The current is changed. Square times 0.08. So the power loss here equal to 3.32 kilowatt. So you see here there is a significant drop of the losses. And this is why we prefer all the time to have a very high power factor, ideally equal to 1. I have a first bonus question to you. When do you think that this is a first point bonus question. Let's see your answer. See who is, guys, get ready. Okay. Okay. Now the bonus question. When you think we will have a power factor equal to 1, which is the optimum, which is the best thing. When you can have a power factor equal to 1. What do you think? What scenario you will have so that the power factor will equal to 1? Okay. We don't have DC. We don't have DC. This is AC. So what scenario, what type of load will give me? Okay, so again, what is the type of the load? So when the theta are the same, if the angles, when we have resistive, excellent row, you got it, row. Okay, when we have a resistive load, but I told you that the nature of the loads at our house is mixed. It is resistive and inductive. Okay, so to have a power factor equal to 1, and this is the first 0.5, I'll give it to Ro. Please send me your email. Now, the second question is, how do you think that I can get rid of the inductive load? How I can have a load that is almost only resistance? How I can do that practically? What do you think? What should I do? What should I add? Add capacitive load. Excellent, Grace. Excellent. So this is the objective of the capacitor. The capacitor, we don't have them in the home, but we add them in the network. Why? To cancel the inductive load. So because they come up with the minus sign, so they will cancel the inductive load, and then we will not be able to have 100% pure resistive or completely canceled inductive, but usually we have 0.9895 power factor. That is very typical by adding those capacitors. How to do the calculation of that, we will not talk about that. This is a more advanced topic, but this is just for your imagination, because we studied the inductor and the capacitor. We always said about the loads are inductive. Then what is this capacitor is doing? The capacitor is doing what is a correction to the power system. We added deliberately to the network so that it will cancel the impact of the inductive load. So excellent job, Grace and Rob. Please send me your emails with your ID, so I will give you 0.5 bonus each. With this, we are done with all numerical types of problems in the course. And I said the last thing we'll have on Thursday, nice chat, if you may, about smart homes and the future of the home and the construction business, and the future of the sensors in our homes, the future of the energy consumption in the home, how we make it more smart, etc. So we'll talk about all of this in next class on Thursday. Thank you guys very much, and I will stop here the recorder.